Hello everybody, this is Todd Frazee and this is the uh, video tutorial for the Sterling 60 or S60-125 part. Okay, we're going to start and by opening our model file that we've made in a prior assignment, which is the 125. Here we go. So we're going to set up this part. And remember, the z-axis is the orientation of whatever the cutting head or spindle is. So right now, Z is pointing at the end of my part. And that's not how we want to do this. Okay, so we start off, we pick on CAM, and we're going to create what's called a job. In Fusion 360, that is the equivalent of a setup. It's the same thing, different terminology. So I'm going to create a new job, and it's going to embed this information in your SolidWorks file. Okay, so we're going to do a job type that's milling, and it automatically selects the model. Now we need to come down and we're going to go out of sequence on this menu here. We're going to scroll down past stock and ignore that for the moment because we need to set our work coordinate system first. And this is the orientation of the machining. So no matter how this was modeled, you can change it, and it's for good reason. So I'm going to rotate the model first to be in an orientation. It's still a 3D orientation, but where you would be viewing it, say, from the machine controller on the right, looking down at the table in an isometric. So what we see as the longest direction would be our x-axis. The short direction would be our y-axis, and straight up and down with the spindle orientation would be in Z. We want to readjust this origin to reflect that. So this is how we do it. We're going to go to, right now it's orientated as if the front plane and we're going to use a z-axis and x-axis reference to change the plane that we're in. So it's defaulting to the front plane. We're going to highlight that and delete it, and we're going to select the top face of the part. So that resets our z-axis normal or 90 degrees to it, and then we're going to select which direction is our x-axis going, and we just pick on an edge, and then we've got our x-axis. Now I think that's backwards. Positive x is going to be to the right, so we're going to reverse the direction of the x-axis. We now have the trihedron pointing the correct way. Now you may need different settings than what I have here, but you want to first get it in an orientation that looks like what's shown on the screen here. Now we're going to go to stock box points, okay, and right now it's at top and center. And the way this works is you have all these different corners that you can use, and we want it to be in the bottom left corner, upper corner, and that would be where we'd set the origin on our machine or work coordinate system. So I'm going to try bottom corner 1. No, that's not the corner I wanted. Bottom corner 2, it's going to snap to the opposite side. Bottom corner 3, which snaps over to the left where we want it, and this must be bottom corner 4. Alright, now that we have that established, we're going to scroll back up and set our stock sizes. The reason I did that out of sequence is it's going to ask you where you want extra material around the part. So right now it's at the yellow represents stock material at the limits of the model itself. So we're going to stick with that, a relative size box, because it's a rectangular part. And then we're going to go to add stock to the sides and to all the sides. We're going to add stock to the sides and top and bottom. Okay, so what it allows you to do is, how much do I want to have a side offset? So let's go 1/2 inch. And we get a larger plate. And then on the top, we want an offset of 0, and the bottom an offset of 0. Okay. Now, if you designed a fixture, you can bring in a fixture model. We will cover that in a future lesson. But the advantage of bringing in a fixture is it allows you to denote areas that you don't want to hit, and it'll give you some collision detection. For XY table, it's a flat sheet. You don't really have any collision problems. You don't have clamps. You don't have bolts holding things down. Okay, so we've skipped over stock box points now. We're not going to select a specific machine. We're going to leave that generic, and then we will set up the machine in the post processor. If we set this up ahead of time, it's good for setting some default settings. But unless you're doing repetitive work and you're switching between a couple different types of machines, that's quite a bit of configuration. When we post process, that's what in programming would be called a compiler. It's going to take the work we're doing here in HSM, and it's going to output code for a specific machine. And most of the older machines will only accept a 4-number character program name. Some of the newer ones will take longer ones, but just to be safe, we're going to restrict it to that. So it's just numbers and only 4 characters. So this is part -125. I think I'll just call it 0125. In the program comments, which are notes that go embedded in the program itself that the machine user can read, I'm going to put S60-125. Then the work offset, we're going to leave it alone, and we're not going to use multiple offsets. So the offset, looks like I accidentally moved my origin, so you don't want to do that. It was supposed to be bottom corner 3 there. Okay, there we go. Sorry about that. All right, now that you got all those parameters set, we can hit OK. And what it's doing is now our stock is established. If you see this weird hatching, don't worry about it. That is a rendering convention. That means those surfaces are collinear to each other or coincident to each other, and the graphics can't differentiate which one's on top. So it's just kind of a marbling effect that you get. Okay, now that we've created that first job, and we're going to go all the way to the farthest right icon, which is the CAM manager for HSM. These other 2 are for CAM Works. Here's the job we just created. So it's the S60-125 operations in this job. Okay, now we're going to go to 2D milling, and we're going to use the 2D contour. Okay, and we're going to leave coolant, we'll leave that at default. We're going to go select a tool. Okay, so we're going to select the cutter we just created. Select. And on the left, you're going to get a whole series of tabs. And each of these tabs has to be cycled through to program the part. We don't necessarily need to change anything. For the purpose of this, we're going to leave the feeds and speeds alone. Again, we're using a milling contour to fake a water jet process, so the 5,000 RPM will translate to a pressure instead of spinning, and there'll be a surface speed, how fast the cutting rate will be. We'll leave that at 40 inches a minute, and we'll move on. Okay, so we're going to go to model. So it's asking, well, what is it that we're actually machining? So what we want to do is we want to machine all these larger circles first, because the cutter is small enough to have a lead in on these, and for the smallest holes it isn't. We have to use some different settings. Okay, so we're not going to need to check any of these things. You could have some advanced functions that go in with these check boxes. For the purpose of this part, they're irrelevant. We're going to go to height. So this sets a series of planes from the top of the part for any type of XY cutting machine. So if we see these different planes, what this is the from retract height, and this is the clearance height. So if you had clamps or whatever, and make sure the machine's not moving in X and Y above that plane. So its default is 400 thousandths from the retract plane. The retract plane is where, after machining started, the cutter will move up to where this green plane is before it moves on to its next feature, but it's not quite as high as the retract height. Okay, and so it is 200 thousandths from the top of the stock, which is pretty much the same as the top of our model in this case, since we're not machining the face down. And then our feed height is the same. That's where the cutter's going to come down and start feeding in instead of going at full rapid. Now on a water jet, it doesn't do any of those moves, so it's pretty much just going to move in X and Y. Okay, and the top is the top of the stock, and we're cutting down to the bottom contour, which we selected. So we're going to cut down to where we selected those circles at the bottom of the part. Okay, moving on, we have the offset. So this is cutter compensation, where there are offsets to the right or left of the line. So we're going to do that in the computer, and it's going to offset, and you can have some different settings here for roughing and moving stock away. The only option we're going to select is this one that says smoothing, and because we're doing circular profiles, it puts a tighter tolerance on the code that comes out for those holes. Okay, and we're done there. So we're going to move on to the last tab, which is the linking tab, and we're going to keep the tool down between cuts, allow rapid retract. So the tool will stay down as long as it's within 2 inches of movement. And our lead-in entry, we're going to do 0.02 on the radius. That's going to be at 90 degrees. 30 thousandths lead-in. It's going to be perpendicular. And we're going to put a 0 on a vertical lead in. You wouldn't have that with this type of cutter. And our lead out is going to be the same settings. Alright, we're going to hit accept. And we have what's in yellow is the rapid movements, as fast as the machine can go. Red is feeding in to the material. And the blue is the actual cutting. So as you can see, we have our cutters coming in a circular path, offsetting to the inside of our profile. Okay, next we're going to set up the cutting for the outside, which is going to use the same settings of what we did on the inside. So we're going to program this out of sequence and reorganize it. So we're going to change the name of this. It's a TD contour of inside. Okay, so our next operation is to cut these holes. They're very small. WaterJet doesn't do such a great job at it. We'll probably end up having to go through with a hand reamer. But we're going to go ahead and do the routine here. A 2D contour. Okay, and we're going to use the same tool we've been using. So we're going to leave everything on the first page the same. The second page, we're going to select the inside bottoms. Of our 3 nominally 16-inch holes. Okay, on heights, we're going to leave everything the same. On 2D contour, we're going to check smoothing. And then we're going to go to the last one, which is linking. We're going to allow rapid retract. We're going to keep the tool down 2 inches, and then down here we're going to put in different settings here. So we're going to have 0 is our lead-in entry. At 90 degrees, we're going to put in a 0.0. We're going to do a 10,000th lead-in. And so if we zoom over, we're going to probably blast right in the center with our pierce, come over and go in a circle. Alright, so we have those 3 holes. Now we need to program the outside. So let's take contour. We'll call this number, actually this should be number 2. And it's going to be pinholes. We're going to change contour 1 to say 2 to be 1. Then we're going to do something here. We're going to right click on the first one and we're going to say duplicate. So we just duplicated contour 1 and we're going to move it to the bottom and we're going to rename it contour 3. Outside. Right click on it. We're going to edit it. And we're going to use the same exact toolpath parameters that we used on all those holes, but we're going to change the geometry we're using them for. So if I highlight each of these edges and delete them in this box using the delete key on your keyboard, the end result is we can now select a different geometry like the outside and use it. Now all the parameters should be the same as the one we duplicated, and then we should be able to hit accept, and we have our outside profile machine, the part free from the surrounding stock. Okay, make sure you're saving frequently. I had this crash on me through the lab halfway through this particular part, so it could happen to you too. Okay, now what do we do next? Now we can go to this stock simulation. Simulate will just show all of the toolpath running, but stock simulation will make it look like it's actually machining. Let's highlight the entire job and go back and do that same thing. Stock simulation, and this should start at the beginning of the part. Program in sequence that's actually going to run on the machine. Okay, now it's going to go around the outside. So the parameters are set right now in the rendering so that each individual operation renders in a different color. Okay, and now it's done. Okay, we can close that. So we've simulated it. It looks like what we think it should do. And now you're going to do what's called the post-process. So we select post-process, make sure the entire job is highlighted. And put in the program number for us, our program comment. I kind of don't trust the document settings, so I put it on inches. Okay, and then we need to select the post-processor. So we are going to go over here and we're going to select the down arrow key, and let's output this for we're going to output this for Fanuc. Some people pronounce this Fanuc, but I always pronounce it Fanuc, so I'm not sure which it is. It's an acronym. And the file type is going to be .nc. Now you want to change this output folder to somewhere where you know where it is. So I would suggest that's your H drive. Right now it's going to my user folder, and so that is going to end up being erased when I start over at the lab. But what's important is that you have this output location in a place you know where it is so that you can upload it in your assignment. So I would suggest you hit open folder and you make it your H drive. For demonstration purposes, I'm just going to say it's in my documents folder. Okay, if you don't see this list of posts, you have to go to setup. Just use installed post library and it'll take you to that path, and you should be able to select this Fanuc controller. Now the file that's going to be output, if you select this box here, it says open NC editor file, it'll open it up and you'll see what the code actually looks like. It is just a text file, so if it had an extension of txt on it, it would still work. You could open it in a text editor and modify it. All these posts are going to put a different extension on it. In this case, it's .nc. But in essence, it's just a text file. Okay, so we're going to hit post, and it's going to be the 125. It's going to put it in my documents folder. I'm going to hit save. And this is the actual G code. So we have its tool number, turning the spindle on, motion codes, stuff like that. Okay, so we're going to go ahead and close this editor. And then we go back to our own folder, which in your case is again going to be your H drive. You're going to be looking for this file here. It says it's a .nc file, and that's the file you're going to upload in Canvas on your assignment. That's the only deliverable for this assignment. In the future weeks, we are going to start getting into what's called our setup sheets. Okay, I hope that went well for you, and I'll catch you on the next one.